Hydraulics is a technology and applied science that involves the mechanical characteristics and utilization of liquids. It is based on engineering, chemistry, and other disciplines. Hydraulics is the liquid equivalent of pneumatics, which is concerned with gases. The word hydraulics originates from the Greek word hydraulikos, which in turn originates from hydr, Greek for water, and aulos, meaning pipe. Fluid mechanics serves as the theoretical foundation for hydraulics, which focuses on practical engineering using fluid characteristics. Hydraulics is utilized in fluid power applications to generate, regulate, and transmit power using pressured liquids. Hydraulic themes involve concepts such as pipe flow, dam design, fluidics, and fluid control circuits and are covered in certain science and most engineering courses. In nature and in laboratory experiments, flow may occur under three different regimes: laminar, turbulent, and transitional. Fluid particles travel in layers in laminar flows, sliding over each other, creating a minor energy exchange between layers and occurs in slow-moving fluids with high viscosity. The turbulent flow is distinguished by random movement and intermixing of fluid particles, as well as a significant exchange of energy throughout the fluid. This sort of flow occurs in low-viscosity, high-velocity fluids. The transitional flow is where the flow fluctuates between laminar and turbulent before it becomes fully turbulent. The Reynolds number demonstration is a classic experiment that involves slowly and steadily putting dye into a pipe to visualize flow characteristics. The dimensionless Reynolds number is used to categorize the flow condition. The Reynolds number has numerous practical uses since it gives engineers instant information on the status of flow in pipes, streams, and soils, allowing them to apply the correct relationships to address the problem at hand. It's also good for dimensional analysis and similitude. For instance, if the forces acting on a ship must be investigated in the laboratory for design purposes, the Reynolds number of the flow operating on the model in the lab and the prototype in the field must be the same. The primary objective of the Reynolds number is to provide some understanding of the interaction between inertial forces, or those that continue moving due to Newton's first law that states that an object in motion stays in motion, and viscous forces, or those that cause the fluid to stop flowing due to the fluid's viscosity. The purpose of this laboratory experiment is to determine the Reynolds number as a function of flow rate and to characterize the type of flow of liquid in the pipe. The visualization of flow behavior will be performed by slowly and steadily injecting dye into a pipe. The state of the flow, laminar, turbulent, and transitional, will be visually determined and compared with the results from the calculation of the Reynolds number. This Reynolds experiment is intended to demonstrate laminar, transitional, and fully turbulent pipe flows while also identifying the parameters in which each of these flow types occurs. Prepare all the materials and equipment needed. Start the experiment by positioning the apparatus on a fixed and vibration-free surface. Measure the diameter of the pipe using the caliper. The diameter of the pipe was determined in order to compute the cross-sectional area of the pipe. Fill the reservoir with a dye. The weight density of the dye should be the same as the water. Allow the flow through the glass tube at the desired rate by opening the valve of the glass tube. When the flow is stable, open the inlet valve of dye injector and allow the colored fluid to flow through the glass tube. Observe the appearance of the dye filament in the glass tube and note down the type of flow obtained for that particular discharge. Take a stopwatch and note down the volume of water collected in measuring for certain interval of time. Repeat the above procedure for different discharge rates for 3 trials and calculate Reynolds number for each type of flow. Make sure to record the temperature of the water in order to determine the viscosity and density. Lastly, close the dye injector valve and the water supply valve. Upon doing the laboratory experiment where the Reynolds number as a function of flow was determined, it certainly perceived the interrelation wherein as the water flow rate increases, the calculated Reynolds number arises as well. Having depth knowledge with this is really substantial because the Reynolds number has several practical applications in the real world, as it provides engineers with immediate information about the state of flow throughout pipes, streams, and soils that aids to put in the proper method to solve the problem.